If we drop a piece of stone and a piece of paper from the same height, which one will reach the ground first? In this video, we will use this question to introduce ourselves to ordinary differential equations. Many thinkers, brilliant thinkers, have grappled with this question over the years for centuries. And today we are lucky to have an answer from physics. So let us clarify the question or the problem. Suppose we had two objects. Here we have a set of stones and a paper. And we begin at a height y equals h. And here we use y of 0 because our independent variable will be time. And so this is a time 0. Then we drop the objects and we wait until they fall on the ground. And let us call the ground y equals 0. So our y equals 0 is the ground, and the objects will reach the ground at time tau. So we don't know if the time tau will be the same for the stone and the paper. Furthermore, we are also interested in knowing how the position changes in time. So do they linearly change? Do the positions of the objects linearly change? Meaning, for every increment in time, is there the same increment in position? Or do they change differently? And so, we are actually interested in two questions. First, which one reaches the ground first? And more generally, we are interested in the function y of t. Can we find the function y of t? And the answer to the question relies on this scientific fact that has been verified countless times, that the acceleration due to gravity is constant regardless of whether we have a heavy object or a light object, regardless of whether we have stones or paper. And so, in fact, we can write the acceleration due to gravity as a constant g, which has been measured to be around 9.81 meters per second. And the next question is, how do we find the position y of t from a of t? So if we recall, we call our y of t the position. And if we are concerned about how fast the position is changing, then we are interested in the speed. It is often referred to as v of t, and it is just the derivative of our position function. Furthermore, we can also define a quantity acceleration, a of t, and it is the same acceleration here, as the rate of change of our speed. So how fast is our speed changing? So that is our acceleration. And because that's just the rate of change in speed, we can write it as a derivative, and that's ddt of v of t. But v of t is itself a derivative of y of t. And so if we write it down in terms of y of t, it will look like this. And therefore, we know that this fact here, that the acceleration due to gravity is constant with a value of g, it can be written in three ways. We can write it simply as a of t equals g, ddt of v, ddt v of t equals g, or that the second derivative of y of t is g. So these three things mean the same thing. Now, can we actually solve for y of t given the scientific fact that the acceleration due to gravity is constant? So let's just write down what we know. So we know that this term on the left side is the acceleration, and we know that it is constant. So this is the physical law that we begin with. Then we recall that that second derivative can be written this way as well. So it's just the derivative of a derivative. And now we can actually remove the first derivative by an integration process. So we integrate both sides, with respect to t, and we obtain this indefinite integral. So this is the antiderivative. And so we remove the first derivative, and on the right side we have gt plus c sub 1, where c sub 1 is an arbitrary constant, which we know very well from integral calculus. And then we still have a derivative here, so what we can do is we can integrate one more time to remove this derivative operator, and what we obtain is we have y of t equals 1/2 gt squared plus c sub 1t plus another integration constant, arbitrary constant. And what we see is that from this knowledge, from this physical law that we had, we are able to obtain the position function, y of t. And this is what we wanted from the very beginning. And so we can say that we actually solved our problem of wanting the position function. And so these three things here, the first three equations, they contain derivatives. Here it contains a second derivative, here two first derivatives, and here we have one derivative in the first order. And so we call these equations with derivatives differential equations, or DEs. And this y of t, which is a function that satisfies our initial differential equation, and also a function without derivatives, we call it the solution to the differential equation. And this is what we mean by solving a differential equation. We are looking for a function that satisfies the differential equation and at the same time does not contain any derivatives in itself. Now we notice that in this very first differential equation, we have an order of 2 in the derivative. And here we have an order of 1 in the derivative. And it is useful to actually make that distinction. So this equation is called a second order ordinary differential equation, or ODE. The word ordinary will be explained in a minute, but the important part here is order, second order. The order means the highest derivative that is contained in the equation. And so this one here, the highest derivative is just 1, and so this is a first order ordinary differential equation. The natural next question is, what if we had an nth order derivative? And so we will call that an nth order ordinary differential equation. So we just need the highest derivative. And this is what we mean by the order of the differential equation. So why do we call this ordinary? We call this ordinary because we have ordinary derivatives here. So are there non-ordinary derivatives? Well, the other type of derivatives is partial derivatives. And so, for example, this equation here is a partial differential equation of the nth order because we have partial derivatives. And now let's look at the solutions. The solutions, or in this case, first, this solution has two arbitrary constants, c sub 1 and c sub 2. These arbitrary constants are artifacts of the integration processes here and in a second integration process. And we did integrate twice because we have an order of 2 here. And so that is the significance of the order of a differential equation. If you have an order of 2, then you expect to have 2 arbitrary constants. If you have an order of 1, you expect only one integration constant, or rather arbitrary constant. And if you have n, if you have an order n, then you expect n arbitrary constants. Now, we know that for any value we choose for c sub 1 and c sub 2, this equation, this function will always satisfy this differential equation. It will always be a solution to the differential equation. And so we call this a general solution because this is the most general form. You can change whatever value, whatever value your c sub 1 and c sub 2. Now, in many cases, we are given a differential equation and a set of conditions that must be satisfied. And those sets of conditions will allow us to narrow down the values of c sub 2 and c sub 1. And so we are able to get a more specific solution. We call it a particular solution. So in this case, because of the conditions that we are given, we cannot use any other c sub 1 and c sub 2. And the lesson here is that for a problem involving differential equations, if you are not given conditions, then all you can get is a general solution. But if you are given more conditions, then you can get a particular solution which is more specific to the given problem. In the previous slides, we've seen how to write as differential equation the fact that the acceleration due to gravity is constant. And in fact, differential equations are very important in science and engineering because the laws of nature are written in differential equations. Here are some more examples. Newton's second law is often written in this way. It says that the force is equal to the first derivative of the momentum. And this is a first-order differential equation, and in this case it's an ordinary differential equation. There are no partial derivatives. Now if you think about the vibration of a spring when you stretch it and let it go, that can be modeled as follows. Here we see that this is the acceleration of the spring, and here is the speed of the spring. So we have a second-order derivative and a first-order derivative. And therefore this is a second-order differential equation because the highest derivative is 2. So we only look at the highest derivative when we're talking about the order of the differential equation. And we also notice that there are no partial derivatives, and so this is a second-order ordinary differential equation. Then here we have the wave equation. So we see that it has partial derivatives. It contains partial derivatives here and here. And again, it is of the order 2. And therefore, this is a second-order differential equation. And to be more specific, second-order partial differential equation. And from the name, wave equation, we can actually guess that this describes the motion of waves. So in physics, if we try to deal with waves or waving motion, we actually use this equation. For example, when we explain the wave nature of light, it will be in this very similar, in an equation that is very similar to this. And lastly, we have the heat equation. It looks like this. So we have a first-order partial differential equation, or rather a second-order partial differential equation. And here we have a first-order derivative, partial derivative, and here we have a second-order partial derivative, and that's why the whole equation is second-order partial differential equation. And this is called the heat equation because by solving this equation, we can actually get the heat profiles. So this is how the heat distributes in space and time, and so that's why it's called the heat equation. In this video, we've learned that differential equations are just equations that contain derivatives, and that they're very important in science and engineering because the laws of physics and nature are written in differential equations. We also classify DEs according to their order and whether they are ordinary or partial. The order of a differential equation is the order of the highest derivative that it contains. It is a partial differential equation if it contains partial derivatives. If it contains ordinary derivatives and no partial derivatives, we call it an ordinary differential equation. We also looked at the solution of a differential equation. To solve a differential equation means to find a function that satisfies the given differential equation and does not in itself contain derivatives. So that's what we mean by a solution. And so to find a solution, we do some integration processes. And as with any indefinite integrals, there will be arbitrary constants. And the solution, in its most general form, will have arbitrary constants, and so we call that the general solution. When we are given more information so that we can eliminate the arbitrary constants and find more specific values, more particular values for the constants, then we are able to obtain a particular solution. These are solutions where the arbitrary constants are now eliminated and we have just a very specific solution or a particular solution. In the succeeding videos, we will familiarize ourselves with differential equations with known solutions. So we will try to learn what most or many mathematicians and physicists and engineers before us have learned.